Thanks. So I hope I'm audible. I'm told that sometimes my voice goes up and down. So if you miss something important, please just feel free to pipe in and let me know. So one of the issues of following a great talk like what Aris gave is that he's covered some of the introduction I had in mind. So which is good and bad because he's probably done a better job than I will. But I can draw on it, I can build upon that. So this is work done with Varsha Dani and Abhi Ghosh, who are visiting TIFR at various points of time. The results are a subset of the results that appeared in 2 papers in AAAI and FST. Okay, so let me get started. So let me start with an example. In my example, there are 4 voters, and the 4 voters amongst them have to choose one from amongst a set of 3 candidates to construct. They can choose to construct either a garden, a library, or a children's playground. And as Aris mentioned, I'm gonna assume that there are these underlying cardinal utilities. So every agent has a numeric utility for each of the candidates. And so the first agent, for example, has utility 0.4 for the garden, 0.6 for the library, and she doesn't like children's playgrounds for some reason. This is true for all of the other voters. Now, I'm going to make the unit sum assumption, which Aris also mentioned, in that if you fix a voter, if you look at the sum of her utilities over the set of candidates, this sums to 1. Right? It's a kind of normalization assumption. It means that the voters are all comparable in some sense. And my goal is going to be the social welfare or the total utility. I would like to maximize this. Now, again, if I have access to all these utilities, my life is very simple. I pick for each candidate, I sum up the utilities over the set of voters, and I pick the candidate which has the maximum total utility. Okay, now I'll tell you why that's not so simple. Life is not so great and easy. Before that, let me just set up some notation. I'm going to use N for my set of voters and N for the number of voters and M for the number of candidates. I'm going to use U sub ij for voterized numeric cardinal utility for candidate J. So the first subset is the voter I. I'm always going to use I prime, so on for voters. And the second subscript J prime or whatever is going to be for the candidate. And as I mentioned, I'm always going to use this, for the most part, I'm going to use this unit sum assumption, which also means that if I sum up all the utilities over the voters and the candidates, I'm going to get the number of voters, which is N. And I'm going to use this U bar to denote the number, to denote the vector of utilities. And that's my goal. I want to select the candidate J, which is maximum total utility. As I said, if I had access to these utilities, life would be simple. There are many reasons why life is not so simple. So firstly, for example, voters are strategic. They may not be truthful. They may not be willing to tell me exactly what their utilities are. Secondly, they may not even know their exact utilities. I mean, assume that they exist, these underlying cardinal utilities. That doesn't mean that voters can actually express them. Or even if they do know them, they don't want to spend half an hour in a polling booth just listing out exactly what their 0.366 is the utility for this 27th candidate or something like that. So there are many reasons why this is not, life is not so simple. Having said that, this is exactly what I'm going to look at in this talk. So, for one part of the talk. So I'm going to look at cardinal mechanisms wherein voters are actually asked to input their numeric utilities for the set of candidates. I'm also going to look at ordinal mechanisms, which Aris also mentioned, which is when agents actually input a preference order over the set of candidates. And I'm going to look at randomized mechanisms where the mechanism outputs a distribution over the set of candidates. I'm going to be interested in the expected social welfare or the expected total utility. Given a preference order and a vector of utilities, this is just what you think it says. It says that agent I prefers J to J prime if and only if its utility for J is strictly larger than its utility for J prime. And I'm going to make the simplifying assumption that there are no ties for a voter just to keep life simple. Okay, so just to kind of flesh out an example further, and a cardinal mechanism will see numeric utilities, an ordinal mechanism will just see this ordering. Right? You'll see that for the first voter, the first preference is the library, second is the garden, and so on. Based on this, an ordinal mechanism is tasked with the objective of trying to find out the candidate which has the maximum social welfare. Okay, as the title mentioned, I'm going to be interested in truthful mechanisms, right? What, given the constraint of truthfulness, what can we achieve on the social welfare? Right? How restrictive an assumption is this? There are a lot of previous work which showed that it's quite restrictive. We want to look at it from the context of social welfare. The definition is, again, sorry, there's a bunch of notation on the slide. The definition is what you think it is, which is that for an agent I, deviation should not improve that agent's expected utility. So if an agent has utility UI, deviating to UI prime, no matter what the other voters are reporting, should not improve her total utility, and similarly for ordinal mechanisms. So, right, this is the definition. And the quantity we're going to measure this loss of social welfare is the distortion. And for cardinal mechanisms, my loss of social welfare is going to be entirely due to truthfulness, the constraint of truthfulness. Without this constraint, I would just be able to easily get the candidate which has the maximum social welfare. For ordinal mechanisms, my loss is going to be because of two factors. Firstly, truthfulness, and secondly, because of the input format. The fact that there is already this information loss due to the fact that voters can only input their ordinal preferences rather than the cardinal utilities. So this loss is what I want to measure. And again, the distortion for a mechanism is going to be, in the worst case, over all instances of the maximum social welfare of any candidate in the instance, divided by the expected social welfare obtained by the mechanism I have, by the mechanism. It's not hard to see that this is at least one. A distribution can't be the maximum utility of a candidate, and the closer it is to one, the better. So I'm going to be interested in mechanisms which have low distortion. The closer to one, the better. So let's take a look at some simple mechanisms and try and understand the distortion of these mechanisms. So the first mechanism is very simple. It doesn't even look at the input. It just uniformly at random picks a candidate and returns it. Since the total utility over all candidates is n, it's not hard to see that the expected welfare of this mechanism is n over m. And therefore, the distortion is just going to be m. Right? This is right. The second mechanism does something a little more interesting. It and I guess again, both of these mechanisms were were shown by Iris as well in his talk. It picks a voter I uniformly at random. It then looks at the most preferred candidate for this voter and just returns that candidate. And again, it's not hard to see. I think Iris showed this as well. I forget exactly, but that the distortion is at least m, and in fact, m you can show is I think asymptotically a tight bound. Both of these mechanisms are ordinal and truthful. So the first mechanism obviously doesn't even look at the input, so clearly it's truthful. The second mechanism, well, if you're the candidate, if you're the voter picked, then you should actually tell the mechanism truthfully what your most preferred candidate is. The third mechanism does what we were doing initially, which is that for each candidate, it's going to sum up the utilities over all agents and pick the max utility candidate and return that. This is also known as the range voting mechanism or the max mechanism. This is cardinal because I'm summing up utilities. This is not truthful. Agents have incentive to lie for this mechanism. And the fourth mechanism I'm going to look at kind of generalizes the first two. So here I still pick a voter uniformly at random, but I have some fixed range of distributions in mind for my mechanism. And what I'm going to do is that I'm going to, from this distribution, I'm going to pick, from this range, I'm going to pick the distribution which maximizes this agent's expected utility. So for example, if my range is the entire simplex, it's a set of all distributions over the m candidates, then actually I just get the second mechanism because the maximizer is always going to be the one which picks the most preferred candidate. It's going to be that point distribution. On the other hand, if my range just considers of this one distribution, the uniform distribution, then I get back the first mechanism, right? So there's some kind of generalization of these first two. And again, these will pop up later. pop up later on in the talk as well. Okay, so we have some mechanisms in mind. Let's try and understand what's known about these mechanisms. So for ordinal mechanisms, it turns out that, that we know quite a bit. So on distortion, it's known that any ordinal mechanism, even ignoring truthfulness, just because of this loss of information due to moving from cardinal to ordinal, has a distortion, of at least omega of square root n. And there exists an ordinal mechanism which has distortion order of square root m log n. So except for this log m, sorry, except for the square root log m factor, this is nearly tight. Ordinal mechanisms, forget truthfulness, just because of this translation from cardinal to ordinal, we already lose the square root m bond. We already lose the square root m factor. And ordinal mechanisms, in another sense, are also very well understood. We have very good characterizations for truthful ordinal mechanisms. So, and this will, and let me just put some definitions before you. These are very natural definitions for characterizing ordinal mechanisms. So for example, I'm going to say an ordinal mechanism is not perverse, is non-perverse, if you fix a voter and if you move a candidate up in that voter's preference order, that does not decrease the candidate's selection probability. It's a very natural condition. Right? This is called non-perverseness. I'm going to say an ordinal mechanism is localized if, on the other hand, supposing you change the positions of some candidates lower down in a voter's preference order, then this does not affect the probability of selection of any candidate higher up. So the change in probability distribution and so on is going to be localized. Okay, so let's just take a quick example. So here are two preference orders. The second one switches the position of D and E. Now what non-perverse means is that because E goes up in the preference order, its probability of selection cannot decrease. Localized means that because D and E are still below A, B, and C, therefore the probability of selection of A, B, and C does not change. So this is what I mean by non-perverse and localized. And what's known in this seminal paper by Gibbard is that an ordinal mechanism is truthful if and only if it is both localized and non-perverse. Right? So these two conditions characterize truthful ordinal mechanisms. And in fact, building on this, Barbara also shows some stronger characterizations for truthful ordinal mechanisms. So truthful ordinal mechanisms are very well understood. This is not true of cardinal mechanisms. So cardinal mechanisms, before our work, I don't, as far as I know, there's not a lot known about the distortion. For characterization, we knew of some very interesting special cases. So we knew, for example, that if the mechanism is continuously differentiable, then it has to be a distribution over unilateral mechanisms. And the unilateral mechanisms, well, a unilateral mechanism is one which basically just depends upon a single voter. It fixes a voter I, and no matter what the other voters do, its output just depends upon what this single voter is doing. And then you can take a distribution over such unilateral mechanisms. It's also known that any Pareto-optimal truthful mechanism is also a distribution over unilateral mechanisms. So if you place these conditions on the mechanism, then in fact, we know that it has to be a distribution over unilateral mechanisms. Okay, so with this, let me jump into what we show. For ordinal mechanisms, we show firstly, for example, in fact, we kind of modify the mechanism which was presented in the earlier paper by Boutillier et al. To show that it can be made truthful. And the same bound holds, so we show a truthful ordinal mechanism which has a distortion of order of square root m log n. And in fact, we show that this holds even for the case we have to select not just one winner, but k winner. And I'm looking at the sum objective over here. Since Aris mentioned it, in fact, for participatory budgeting, we show that the same thing gets square root m log m, except that log m is now outside the square root. And we show that this is tight for truthful ordinal mechanisms. that in fact, if you, in addition to ordinal, you impose truthfulness, you lose an additional square root log m factor. And this is a tight bound. For cardinal mechanisms, well, we found this somewhat surprising that in fact, any truthful cardinal mechanism also has distortion omega of square root m. So here there is no loss imposed because of the translation from cardinal to ordinal utilities, right? It's all cardinal. So in some sense, the mechanism has access to a lot of information, but just truthfulness itself is enough of a constraint that the distortion is omega square root m. Now note that there already exists a mechanism which has distortion order of square root m log m, right? This is just the ordinal mechanism. However, we wanted to come up with a different cardinal mechanism as well. And this is what we also show. We give an order of square root m log m distortion mechanism that is cardinal, and it particularly violates the two conditions of truthful ordinal mechanisms. So, so I define these conditions for ordinal mechanisms. They kind of translate naturally to cardinal mechanisms as well. So perverseness just means that it can happen that a voter increases the utility for a candidate. However, the probability that the candidate gets selected actually decreases. Similarly, localized also has natural translation, and our mechanism kind of violates that as well, despite the fact that it's truthful and gets a good distortion log. Okay, all right. Now, given the fact that truthful mechanisms don't work too well, we were also interested, well, you know, what if you look at Equilibria? And I thought this was a nice result. The point is that, you know, the range voting mechanism or the max mechanism. So we show that for a particular equilibrium, which you obtain through a natural dynamics, actually has distortion close to 1. So there's a simple deterministic mechanism which has distortion close to 1. And not for all equilibria, certainly, you can have very bad equilibria. But for a particular equilibria, which you can obtain through natural dynamics, the distortion is close to 1. Okay, cool. So in this talk, I'm going to talk about the upper bounds mostly. I'm not going to talk about lower bounds. But hopefully that will give a good idea. I should mention that these papers have some other results as well. Aris mentioned this thing about the threshold voting. That's something I'm not going to talk about, but it is in the first paper on ordinal mechanisms. So, okay, so let's talk about this. And this is the mechanism. It's a slight variation on the mechanism which Aris had mentioned and the mechanism in the Boutillier et al. Paper. In particular, those earlier mechanisms, instead of, okay, so what is the mechanism? The mechanism just tosses a fair coin. If it comes up heads, it just picks a candidate uniformly at random and returns it. If it comes up tails, then it chooses a random voter I and returns the candidate rank J by this voter with probability proportional to its rank, proportional to the inverse of its rank. Okay. And the slight variation is that in the earlier mechanism, instead of picking a voter I and looking at its ranking of candidates, it looked at some aggregate ranking and kind of did something similar, but that was not truthful. This you can show is truthful and gets the required bound as well. It's not hard to show that it's truthful. Just if you think about it for 2 minutes, you should get it. The distortion is slightly more interesting, and in fact, this analysis pops up later on as well. So let's just do it. So I'm going to look at two cases where opt is low and opt is high. In the case where opt is low, let's say by low I mean it is at most n, which is the number of voters, times square root of log m by m. Well, in this case, since the optimum social welfare is low, actually our first mechanism, which just picks a candidate uniformly at random, does well enough. Right? It gets a welfare of n over 2m. You divide the two, you get the bound on distortion. In the second case, where opt is at least n times square root log m over m, so we'll show that we in fact pick the optimal candidate with high enough probability. So if J star is the optimal candidate, well, here's a small fact that because of my unit sum normalization assumption, the utility that J has is at most 1 upon its rank, because at least, you know, all the candidates before it, which is the number of those candidates is its rank, must have at least as much utility. And the sum is 1, so I get this inequality. And then what is the probability that J star is selected? Well, for each voter, it's probability that the voter is selected times the probability that J star is selected given that I is selected, which is exactly this expression. If I remove the proportionality, I get approximately log m. Yeah, and if I plug in the utility in place of the rank, this is what I get. So the probability that J star is selected is at least its social welfare divided by n log m. And for distortion, I know that it's at most, the social welfare of J star divided by the welfare I just get from J star. And this is an upper bound because I could select other candidates and they will also give me some welfare. Let me ignore that. I'm just going to look at the welfare I get from J star. So that's the welfare of J star times the probability that I selected. I plug in things and I get the required result. Right, and I said we're going to do some similar analysis later on as well. Okay, so right, so this mechanism, the harmonic mechanism, is great. It's truthful. It has a distortion of 1 over square root m log m, and as we said, this bound on distortion is tight. So let me talk about a cardinal mechanism now, which obtains the same bound but does something interesting. And before I jump into this, I want to mention that, like the reason we looked at, this mechanism, even though the bound is not new, is that we wanted to see if a mechanism which violates this localization and perverseness, is non-trivial, can actually get a good bound. And that's what we show. So let me show what the mechanism is. It's inspired by other mechanisms studied by Barbara and other papers as well. So like I said, I'm going to have this range of distributions and I'm going to pick a voter I uniformly at random and pick a distribution from the range to maximize the voter's expected utility. For 3 candidates, I can represent my distributions, the simplex, as this triangle. And this is what my S is. It's the circle which lies within the simplex. This is my utility. Then, I'm like kind of ignoring some details. This is roughly what what the mechanism should output. It picks the point obtained by drawing this line, and that's my P. And the next few slides kind of give a numerical example to show that this mechanism is not localized and is perverse. Let me skip that. So I'm going to skip just this example which shows that it's not localized and is perverse. Okay, so we talked about 3 candidates. Now the point is that if we have more candidates, the inscribed circle, the radius goes to 0. So it just more and more just looks like the uniform distribution. So instead, what we're going to do is we're going to allow larger radii than that of the inscribed hypersphere, except that we will truncate it. Right? So this is what my truncated hypersphere looks like. I mean, I fix the radius and I do this. It's characterized by the radius r. And here's the thing though, that if you fix a radius, then any mechanism of this type actually has a distortion of omega of m to the 3/5. So we do the natural thing. We randomly choose the radius of my truncated hypersphere. So let me do this. So this is what my set of radii looks like. I randomly pick a radius from this. And on this truncated hypersphere, I find the point which maximizes the expected utility. There are log n choices of radii, and note that they increase by a factor of 2 every time. And this is also truthful, has a distortion of order of square root m log n. So again, truthfulness is easy because I'm choosing a distribution to maximize the voter's expected utility. What about the proof of distortion? So the first case is exactly similar to previous one. If opt is low, then the first step where I uniformly choose a candidate and return it gives me the required distortion bound. Second case is slightly more interesting. So again, we will show that the probability will show exactly the same bound, right? The probability that the optimal candidate is selected when the social welfare is high enough is at least opt over twice n log m. And if you show that, then again, by the same analysis, you get that the distortion bound is square root m log m. Right? So what we want to show now is that even for this mechanism, the probability that J star is selected is at least opt over twice n log m. And here's why this is true, right? So basically, so now because the radii double, so what happens is, so you fix any utility and you look at half the distance from the midpoint to that utility. Now, because the radii increase by a factor of 2, some hypersphere lies between ui and ui by 2. Now, this means that for all candidates J for this hypersphere, the probabilities must be at least uij by 2. And because of that, well, you can kind of, write down the formula, write down the numbers, and you will get what you want. Right? So the doubling of radii is exactly what gives us what we want over here. Okay, cool. So that's my hyperspherical mechanism. It has a required distortion bound. It violates some natural conditions, but it works. Okay, so lastly, I guess I want to quickly talk about Equilibria. Right? So this is the max mechanism. We talked about it. You pick a candidate which has the highest utility. And if there's a tie, you just choose a candidate with a higher index. Right? You have some ordering of the candidates. You pick the one which is higher up in the order. And here are the dynamics that we look at. So initially, each voter reports utilities truthfully. And if a voter wants to deviate, then the only way it can deviate is basically by shifting to ones and zeros. Right? So whichever candidate wants to win, it gives it utility 1. Everybody else, it gives it utility 0. So it puts all its weight onto the new winning candidate. So we call this binary voting dynamics. And in fact, we show that this converges to a pure Nash equilibrium with distortion opt over opt minus log n. Right? So this is very, very close to 1. So this is a proof of convergence. In fact, it converges in something like n cube steps. Let me skip the proof. I think I'm almost out of time. Right. So this is a proof for the distortion as well. I'm going to skip the proof over here. But I mean, yeah, like we thought it was nice that, the simple mechanism with this binary voting dynamics, which is natural, we thought actually gives you a good distortion bound. Okay, so just to recap, those were other results. For ordinal mechanisms, there are tight bounds. For cardinal mechanisms, there's this log m gap, but we get good results for Equilibria. And let me just put 2 slides on open questions. So firstly, there's a small gap. There's a square root log m gap. I think that's an important gap. I think that to close that gap, you need to have better characterizations of cardinal mechanisms, truthful cardinal mechanisms. So I think that is an interesting question. And secondly, we would like to have better results for approximate truthfulness and Nash equilibria as well, particularly other dynamics. The second open question. So we noted this unit sum assumption. You can instead have a unit range assumption, which states that all utilities lie in the interval 0 through 1, such as that shown here. And just that for every voter I, there are 2 candidates L and H for which its utilities are 0 and 1 respectively. That's true for this example over here. Right? So if you have 3 candidates, the only parameter that matters is the utility of the middle one, because the others I know are 0 and 1. For this, for these kind of normalizations, unit range normalization, it's known that again we have tight bounds on ordinal mechanisms. However, for cardinal mechanisms, there's a large gap. We know an upper bound of m to the 2/3, a lower bound of log m over log m. So yeah, this would be an interesting question to solve as well. Let me just stop here and say thanks.